Welcome back, ladies and gentlemen. Here we go, looking at an example of how to solve a circuit. This one is a combination or compound circuit where you see resistors both in series and in parallel. And these are our objectives for what we're going to try to figure out. Now, you won't always be asked to do all of this for a circuit, but this is all a possibility. Looking at the equivalent resistance or the overall resistance of the circuit. In other words, if we were to view this circuit as just having one resistor, and that one resistor had a resistance that was equivalent to all this stuff, so this would be like our REQ, then what would that resistance be? Okay, we're going to figure that out. We're going to figure out the overall current. Now, in this circuit, the overall current you should recognize is flowing in sort of a clockwise direction. Label I there. And we want to figure out the value of that overall or total current. Sometimes it's called the current through the battery or terminal current. I just call it the overall or just label it capital I. We also want to figure out the individual voltage drops across each individual resistor. So what is the voltage drop across R1, across R2, and across R3? And there's some interesting stuff we know about the voltage drops here compared to the voltage gain of your source. Vs is voltage of the source. That could be a battery, it could be a power supply. We also want to look at individual currents through each resistor, R1, R2, and R3. And there's a couple things we can see before we do any calculation there. And finally, we're not going to do the energy dissipated by each individual resistor, but we'll look at one example, resistor number 3, and see, well, in 5 minutes time, how much energy would R3 end up using. That's our plan here. This will take a fair bit of work, but I'll lay out the steps as clearly as I can for you. And I'll keep coming back to this list and also to this diagram. But we're going to redraw it once or twice to make things easy to follow. So here we go. You paused. You want to make sure you have this drawn out, and you probably also want to have these questions, but you'll see the questions all come up. I'll rewrite them. Okay, here we go. We're good to go. I'll keep this one handy because I want to come back to that diagram over and over. One of the first things I want to do is, this is a personal thing for me, I want to redraw that circuit. And I want to redraw to model the waterfall, or to match the waterfall. Okay, so that's what I'm going to do right here. And so I have a voltage source here. Well, all I'm going to, essentially, in order to model the waterfall, look what I have to do. I just have to rotate this, because now you can see that the voltage source is like the water pump, lifting and adding energy to the charges. That's what the battery or power supply will do. And then as the charges flow this direction, they're giving up energy, they're losing energy. And then they're going to flow back and be charged back up, so to speak. That's really a misnomer, but they're going to be energized, let's say that. Okay, and over and over and over, right? So this side is like the water pump, this side is like the waterfall. Well, I want to draw it like that so I can be thinking about energy in and energy out. So I've got my voltage source, and we have a split, and we're going to have 1, 2, 3, and back to my source. Okay. And so you look at this and you go, well, wait a minute. You switch those around. So see, on the outside I have the individual resistor R1, and I put on the inside here. That actually doesn't matter. It doesn't matter that I put this pathway on the left or the right. It's still the same pathway. So let me get a few things labeled so I don't lose track of what's going on, right? Voltage source, and this is 12.0 volts. This will be R1, R2, and R3. And this is going to be 300 ohm. No, sorry, R1 is 200 ohms. R2 is 300 ohms. R3 is 100 ohms. It would have been easier to remember if I had 100 for 1 and 200 for 2 and so on, but this is what we have. Okay. Oh, and the current, like, remember the current is going to flow this way and then down here, and it's going to keep going. It'll split and go through individual pathways. Now, one of the neat things about doing it this way, as I mentioned, you can look at a voltage gain here. And here, as things fall down, you have a voltage drop. And what that means is here is energy in, and here is all your energy out. All your energy that is removed from the charges happens over here on the resistors, and all your energy added to the charges happens over here on your voltage source. Cool. All right. So I've got the redraw. This is not at all a required step, but I personally like to do it. So I'll come back to that again as well. So now we got to get to the first task on our list. Overall resistance, equivalent resistance. So I'm going to find REQ. And there's sort of a I don't know, a way of thinking about this. I need to start in at the smallest possible combination of any two resistors and work my way outward. So you have to ask yourself this. I have R2 and R3 that are in series with each other, one after the other. I have R1 and R2, which kind of look like they're in parallel. If I do this, they really look like they're in parallel. But I also have R1 and R3, which look like they're in parallel. So where do I start? I can only start with any two resistors. And so here's what you must do. You have to just say, well, what are the closest pair that I can pick? The most local, the most the pair with the least interference from anything else. So okay, if I have to look at 1 and 2 by covering another one, by covering 3, then 3 is kind of interfering with that parallel nature right there. So that's not the closest, that's not the simplest combination. Same thing going on here. If I have to cover R2 to consider R1 and R3 in parallel, well, R2 is interfering a little bit with that. Well, look at this. What about R2 and R3? If I cover R1, do I have to do this to see R2 and R3 are in series with each other? Because if I do this, are R2 and R3 still in series? Clearly they are. So that's what I'm going to pick first. Okay, and so what I'm going to do is look at those two, and I'm going to come up with an equivalent of R2 and 3 combined. That's the first step that I have to go through to get here. So I start small and work my way in. So now I'm going to find R2, 3. And so the rule about series resistors is you simply add the resistances together. So I have R2 plus R3. And that is going to be 300 plus 100. And that's 400 ohms. Easy right there. Okay, so 300 plus 100, 400 ohms. Now, the next step is to make this clear, I can do a quick redraw and say, well, you know what, I got the source. So now I have two pathways. That pathway and there's this pathway. Essentially, okay, not quite drawn the same. You can see the difference, but it's just the wires drawn differently. This is R1. So what is this guy now? This is R2, 3. Okay. Well, I now can clearly see parallel nature between R1 and R2, 3. So when you look at the rules for combining resistors that are in parallel pathways, then the rule is a little different. So now what I'm going to do is I'm going to find a combination of 1, 2, and 3, which will be my equivalent. Once I combine these two, I will have combined everything. So now I have parallel resistors. So the rule is I add, I'm sorry, the equivalent is going to be the inverse of the sum of the inverses. And that sounds kind of convoluted. So I'm going to have the inverse of R1. I'm going to add the inverse of R2, 3. And then I take that sum and take the inverse of it, and that's my equivalent resistance. So 1 over. And R1 is, what is R1? R1 is 200 ohms. So 1 over 200 ohms. And R23, I just found it was 400 ohms. 1 over 400 ohms. And when you do this math, it's not all that difficult. You come up with 133.3 ohms. And we've done the first step. This is the equivalent resistance of the whole circuit. That's an answer I want to put in a box, and I can come over here and I can very happily say, boom, done. Got the overall resistance. There it is. So, moving on to the next step. The next step is going to be finding overall current, and this is very straightforward. Oh, I need some. All right, get some resources together here. So next step, I'm going to find the overall current through the circuit, and this is real simple. I'm using Ohm's Law. So Ohm's Law, current is equal to voltage divided by resistance. Now the voltage I'm using is the voltage of the source, and the resistance I'm using is the equivalent resistance. Straightforward. So that's 12.0 volts, and this is now 133.3 ohms. So what is my current in this circuit? 0.0900 amperes. Put a box around that answer. There it is. If I had just one resistor that had a resistance of 133 ohms and the voltage source was 12 volts, I'd be getting this current. And that's what's happening through the circuit. So I have to keep in mind that is not the current flowing through every part of the circuit, but it's the current flowing through the main parts here where there's no pathways to decide upon, no choices, no junctions. That's what they're called, really. So, good. Now, the next step, next task to accomplish is going to be, I found overall current. Look at that. Check it off. I'm going to find individual voltage drops. And so V1, V2, V3, what this really means is I have a voltage gain from the source here. And each of these resistors provides a certain voltage drop. The source adds energy to the charges. Each resistor removes energy from the charges. That's what a voltage drop is going to mean. So I need to figure out each one. Voltage drop across R1, voltage drop across R2, voltage drop across R3. That's what V1, V2, V3 represent. So that is the next thing. Find V1, V2, V3. All right. So you have to understand what's going on here. I'll bring in this guy. So R1, if you trace back from R1, can you get to, I'm sorry, I should ask it differently. What voltage potential, what electric potential do you get to when you trace back from R1? So as I do this, tracing back from R1, this is gonna just a tracing, like following it back. You know what I get to before I bump into anything else? I get to the 12 volts, and that's kind of significant. That's going to help me understand what's going on here. So there's a way of phrasing that. I can say that R1 sees, quotes, that dot's not supposed to be there. R1 sees the voltage of the source. So the voltage drop of 1 equals the voltage gain of the source, which was 12.0 volts. Okay, so V1 equals 12.0 volts. Already found one of them, didn't have to do any math. And that's kind of cool. So what electric potential is being applied across R1? Well, I can connect there to there. And those two things, that connection for voltage would be the same as if I had connected here to here. Look at what the wires are doing. The wire just connects, so it really wouldn't matter where I put these terminals. I could put them here. I get 12 volts. I could connect my multimeter here, and I'm still going to see 12 volts. Okay. It won't be quite so straightforward for the other two resistors individually, but I can also, by the same argument, say that resistor 2,3, an equivalent resistor, also sees, in quotes, the voltage source. So the voltage drop of 2,3 in combination equals the voltage of the source equals 12 volts. And so there's another way of looking at it here. Again, we say, you know what? If we look at 2,3 in combination, they get the same potential as R1 does. Anything along here, let me use a different color because this is sort of significant. From here, from the source to there, anything along here is all the same potential. All the same. So R1 sees that potential and R2,3 in combination sees that same potential. Okay, moving on. This is not an answer I'm looking for, but what I know is that Ohm's Law says that the voltage across 2,3 is equal to the current through 2,3 times the resistance of 2,3. Okay, what I'm going to have to do is I'm going to have to rearrange this and find the current through 2,3 because I know the voltage drop and I know the resistance. So I can actually look for this guy. That's helpful. You'll see why. I'm going to go to a new page. I'll continue on here. Okay, so real quick at the bottom of this page, I'm going to rearrange, and this is going to be current through 2,3 in combo is voltage of 2,3 divided by resistance of 2,3. And so now, what is the current through 2,3? I have my 12 volts, 12.0 volts, and I have my equivalent resistance of 2,3. 2,3 was, well, that's real easy. That was the 400 ohms, right? Okay, so the current through 2,3, 12 divided by 400, and 0.0300 amperes. So you might wonder why those trailing zeros, significant figures. If I take each of these resistor values to be 3 sig figs, technically they're not. But then I also have a voltage source of 3 sig figs, and I'll just maintain 3 significant figures for all my answers. It's very straightforward. Okay, well, the significance of excuse me, of this is that R2 and R3 are in series with each other, and when resistors are in series, you have the same amount of current flowing through one as you have flowing through the other. They see the same current. So, because excuse me, because I2 equals I3, and it also equals I of 2,3, from that, then what I can do is I can figure that, well, the voltage drop of 2 is equal to the current through 2 times the resistance of 2, right? Because I'm looking for that voltage drop across resistor 2. I am. But look at this. The current through 2 is the same as the current through the whole 2-3 business. So I'm going to substitute that here. And now I know the current and the resistance. I can find the voltage drop across 2. So that was 0.0300 amperes. And the resistance of 2 is 300 ohms. What is the voltage drop across 2? You get an answer of 9.00 volts. Answer. So I have found, so far, the voltage drop across resistor 1 and the voltage drop across resistor 2. I need to do one more. So I'm going to solve V3 pretty much using the same logic as I did for V2. V3 has the current 3 times resistance of 3. That current of 3 is equal to the current of 2,3 right there, and I know that value. So 0.03 amperes, and resistance of R3 is 100 ohms. What's the voltage drop across resistor 3? 3.00 volts. Answer. Okay, and there's something interesting that you should be picking up on. So let's check this out. Voltage drop across resistor 1 was 12 volts. That was equivalent to the source, because if you get rid of that pathway, you still have a complete circuit and it's just through R1. Okay. Well, what if you get rid of this pathway in the middle, right here? You still have a complete circuit through R2 and R3, right? So R2 and R3 combined see a voltage drop equal to 12 volts. Awesome. R2, what did I just say? I said R2 and R3 see voltage drop that's combined to equal the source, which is 12. V2 and V3 combine, 9 plus 3, that's 12. That's equal to your source. Cool, huh? Okay, so watch this. Checking off another thing on my list. Individual voltage drops. Check mark. Done. Next, I want to find individual currents through I1, I2, and I3, or through those resistors. The currents are I1, I2, and I3. Okay, so I need a new paper. And so I1, I2, I3. I want to find those individual currents through each of those resistors. Basically, I'm just going to use Ohm's Law. It's an M. And the reason I want to use Ohm's Law is very straightforward. Now I know for each resistor, I know its individual resistance, and for each resistor, I know the voltage drop of each one. I found V1, it's on a different paper. Here's V2, here's V3. So if I know the resistance and I know the voltage, I can easily find the current for each one. So here's the basic form, right? Basic form of Ohm's Law to find current. And so, well, current through 1 is V1 divided by R1 is, V1 was 12 volts, R1 was 200 ohms, V looks like a check mark, sorry. And so what I get here is 0.0600 amperes. Okay, so quick rewrite, I1 is 0.06. There we go, answer number 1. I can do the same for I2. I got V2 divided by R2. And this is voltage drop across 2. I found that. That was 9 volts. And I'm going to divide by a resistance of 2, which is 300 ohms. Okay, 9 divided by 300, and I get 0 amperes. So another answer. Pretty quick, pretty straightforward. And now here's something to check out. Okay, I'll do it this way. For the current through resistor 3, V3 divided by R3. Voltage drop across 3 was 3 volts. And R3 had a resistance of 100 ohms. Okay, and so I get 3 amperes. And so I'm going to rewrite real quick. I3 0.0 amperes. Okay, answer. Okay, now check it out. You notice about these two answers, they came out the same. So when I'm looking at these two resistors, they have different values of resistance, but they're on the same pathway. They're in series with each other. So the current through this one pathway will be the same current at all points through that pathway. So R2 and R3 each see the same amount of current flowing through them. They have no choice. There's no other no other pathway for the current to take until it gets down here. So from here to here, R2 and R3 are going to experience the same current. It's really just that simple. Cool. So I come back to my list of tasks to accomplish. Check. Look at that. We are nearly there. I need to find the energy dissipated by resistor number 3 in 5 minutes. Okay, so my final step. Energy. Okay, so what I recall about electricity, current electricity, you're dealing with there's voltage, you're dealing with current, and you're dealing with resistance. And well, I recall several things. So number one, I can break down a couple of these. I can say that, well, voltage is energy divided by charge. Oh, I see energy. Okay, current is charge divided by time. Now wait a second. I was given a time, right? I was told 5 minutes. I'm probably going to end up having to use that. There's another relationship here between voltage and current, and it's through power. So power is equal to voltage times current, or current times voltage, same thing. Okay, so what do I want to do? Well, okay, I also know something about power. Power is energy divided by time. So you know what? I actually want to start with this equation here. So find energy dissipated in 5 minutes. That's what I'm doing right here, right now. Okay, I'm going to start with this because I see energy, time, and I know they're related through power. I'm going to rearrange and say that energy is power times time. See what I've done? Just taken from that, multiply. Okay. And energy is my goal. Well, I have a time, 5 minutes. I need a power. Well, a power is coming from this guy, voltage times current. So voltage times current, and I have to do the times time. There's energy. So do I know the voltage drop across resistor 3? Remember, this is for, I'm only doing this for R3. Yes, I do. Do I know the current through R3? Yes, I do. And so I know my time also. So now it becomes a pretty straightforward question to answer. My voltage drop across R3 was 3 volts. The current through R3 was 0.30 amperes. I have a time of 5 minutes. Okay, time out for a second. And the reason is, I see minutes, but base SI units aren't minutes, they're seconds. So I know that there are 60 seconds in a minute. So a little conversion taking place right here. That's an S divided by a minute. Sorry about that. So I have to throw that in there. And when I do this, I find that the energy really this is the energy across resistor 3 in 5 minutes time, is, get out the handy dandy calculator, and I get 27 what? What are the units on energy? That's always going to be joules. As long as you've got base SI units, it'll always be joules. That's how you do it. There's the answer. And so I can check that guy off as well. And of course, I could do the same thing for each other resistor if I needed to. In this case, I don't have to. You can see how once you've laid everything else out, you have all this information readily available, and you easily get to that answer. So, lots of individual steps, but none of them terribly difficult as long as you stay organized as you work. That is very, very important. You can see what I've done in terms of organization here. I lose track of all my papers as I sort of backtrack. 6. I'm identifying what I'm solving for. I've got answers in boxes, right? Here's page 5, which was a continuation of page 4, which is where? Where's page 4? I don't know where page 4 is. 3, 2, 3. Oh, I have 2 page 3s. I've lost my page 4. Oh, it's buried. I got so much going on. Okay, so again, identifying what I'm solving for, answers in boxes, right? And if I back up even further, I can find page 3, which looks like it's right, not over there. 2 page 3s. I'll use this page 3. That looks like it'll work. I think that's the one. And then if I, so again, finding, labeling what I'm finding. Here's page 2 where I redrew the circuit. Here's page 1, the original question. Wow, okay, 1, 2, 3. You can see it's organized. If you stay organized and you write clearly, you will have no trouble with this stuff.